Welcome to this problem walkthrough. Today, we will be discussing problem number 831, masking personal information. In this problem, we are tasked with handling sensitive data and ensuring it is appropriately masked based on given requirements. We'll explore the problem, break it down, and step through an efficient approach to solve it. Let's dive in. In this problem, we are tasked with creating a program to mask personal information provided as a string. The input could represent either an email address or a phone number, and our job is to format and mask the input based on specific rules. Let's first look at the rules for masking an email address. An email address has two main parts, the local name and the domain name, separated by the @ symbol. While the domain name remains completely visible, the local name is partially masked. Specifically, we retain the first and last characters of the local name and replace all other characters in between with 5 asterisks. Additionally, the entire email address is converted to lowercase, and it's important to remember that masking is case-insensitive. For example, if the input is example@LeetCode.com, the output would be e*********** e @LeetCode.com. As you can see, the local name is masked while the domain name remains unchanged, and the entire string is in lowercase. Now, let's talk about the rules for masking a phone number. A phone number can contain various characters like digits, spaces, dashes, parentheses, and even a leading plus sign. However, only the digits are relevant for masking, so we ignore all non-digit characters. Once we extract the digits, we check the total count. If there are exactly 10 digits, the output format is ********************************************************************************************************************************************************************************************************************************************************************************************************************************************************************************************** XX represents the last 4 digits of the number, and the other digits are masked with asterisks. On the other hand, if the phone number contains more than 10 digits, it indicates the presence of a country code. In this case, the output format becomes +C******************************************************************************************************************************************************************************************************************************************************************************************************************************************************************************************* represents the country code, which can be 1 to 3 digits long. For example, the input 1, 2, 3, 4, 5, 6, 7, 8, 9, 0 would result in the output *******7890, and the input plus 8, 6, 1, 0, 1, 2, 3, 4, 5, 6, 7, 8 would result in plus *********5678. These formats ensure that the sensitive parts of the phone number are masked while retaining enough information to recognize the number. The program should return a masked version of the input string based on these rules. Let's look at some examples to solidify our understanding. In the first example, the input is LeetCode@LeetCode.com. This is clearly an email address, so we apply the email masking rules. The local name, LeetCode, is masked to L***********, while the domain name remains unchanged. The output is L********e@LeetCode.com, fully converted to lowercase. In the second example, the input is AB@QQ.com. Here, the local name is AB, which has only 2 characters. In this case, we retain the first and last characters, masking the middle section with 5 asterisks, even though there are no characters in between. The output becomes A*******B@QQ.com, again with the domain name unchanged and the entire string in lowercase. In the third example, the input is 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. This is a phone number containing non-digit characters, which we ignore during processing. After extracting the digits, we get the number 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, which has exactly 10 digits. Following the phone number masking rules for a 10-digit number, the output format is **********7890, where only the last 4 digits are visible, and the rest are masked with asterisks. This ensures that the sensitive parts of the phone number are hidden. In the fourth example, the input is +86 10 1234 5678. This is another phone number, but it includes a country code. After removing the non-digit characters, we get 861012345678. Since the total number of digits is 12, the country code is identified as 86 foot, and the last 4 digits are 5678. The output is formatted as +****************5678, where the country code is partially masked, and the rest of the number follows the same masking rules. To summarize, when processing phone numbers, all non-digit characters are ignored, and the final output depends on whether the number has exactly 10 digits or includes a country code. For a 10-digit phone number, the format is ******************************************************************************************************************************************************************************************************************************************************************************************************************** The format becomes +C*************************************************************************************************̈̈̈̈̈̈̈̈̈̈̈̈̈̈̈̈̈̈̈̈̈̈̈̈̈̈̈̈̈̈̈̈̈̈̈̈̈̈̈̈̈̈̈̈̈̈̈̈̈̈̈̈̈̈̈̈̈̈̈̈̈̈̈̈̈̈̈̈̈̈̈10 represents the country code, masked except for its first digit. In the examples, the input 1, 2, 3, 4, 5, 6, 7, 8, 9, 0 was transformed into **********7890, while +86, 10, 1, 2, 3, 4, 5, 6, 7, 8 became +*******************************78. These examples illustrate how the program handles both standard 10-digit numbers and those with international dialing codes. Finally, let's go over the constraints for this problem. The input string will always have a length between 1 and 100 and will represent either a valid email address or a valid phone number. For email masking, the local name will always have at least 2 characters, and the domain name will include at least 1 dot. Both parts of the email may contain alphanumeric characters, dots, and plus signs. For phone numbers, the total number of digits, after ignoring non-digit characters, will always be between 10 and 13. Additionally, the input will only contain valid phone number characters such as digits, spaces, dashes, parentheses, and the plus sign. These constraints ensure that the input is well structured and can be processed reliably using the defined masking rules. To tackle the problem of masking personal information, we first considered a brute force approach, which involves parsing the input character by character. The intuition here is straightforward: identify whether the input is an email or a phone number based on its format, and then apply the appropriate masking rules. For email addresses, we would locate the @ symbol to separate the username and domain, then mask the username while keeping the first and last characters visible. For phone numbers, the process involves stripping out non-numeric characters, counting the digits to determine the format, and masking all but the last 4 digits while appropriately formatting the output. This approach operates in O(n) time complexity, making it efficient for basic scenarios. However, one significant drawback is its lack of modularity. The code becomes harder to understand and maintain as more formats or rules are added, which increases the likelihood of errors. Overall, while this method gets the job done, it can quickly become cumbersome for more complex cases. Recognizing the limitations of the brute force approach, we explored a more optimized solution rooted in modular parsing and masking. The key idea here is to break the problem into smaller, independent components, each responsible for a specific task. For example, we can use a helper function to classify the input as either an email or a phone number, another to mask email usernames, and yet another to format phone numbers based on their digit count. This separation of concerns makes the solution clearer and more maintainable. The process starts by classifying the input emails are identified by the presence of the @ symbol, after which we isolate the username and domain, mask the username, and recombine the components. For phone numbers, we extract the numeric digits, apply masking while retaining the last 4 digits, and then format the result appropriately. This method still runs in O(n) time but offers several advantages over the brute force approach. It's easier to debug, avoids redundant logic, and can accommodate future updates or additional rules with minimal disruption. The trade-off is a slightly more verbose implementation, but the modularity and clarity make it well worth the effort. Ultimately, we chose the modular parsing and masking strategy because it provides the best balance between simplicity and maintainability. This approach avoids duplicating logic and ensures a clear separation of tasks, which makes the codebase more adaptable and easier to extend. The key insight was realizing that the problem could be divided into 3 distinct steps: identifying the input type, applying the appropriate masking, and formatting the output. Each of these tasks is independent, yet all contribute to producing the final result seamlessly. Compared to the brute force approach, the modular strategy is inherently more robust and readable. While both methods share the same O(n) time complexity, the modular approach significantly reduces the risk of errors and promotes long-term maintainability. When weighing the trade-offs, the brute force method is quicker to implement for small-scale problems, but its tangled logic makes debugging and scaling difficult. On the other hand, the modular approach is slightly more verbose but excels in clarity and flexibility, making it the superior choice for this problem. Given the constraints and the need for correctness and extensibility, modular parsing and masking emerged as the clear winner. The problem at hand is to mask personal information, specifically email addresses and phone numbers, in a way that maintains privacy while still presenting the data in a recognizable format. To achieve this, the algorithm begins by identifying the type of input, whether it's an email address or a phone number. The key operation here is to check for the presence of the @ symbol in the input string. If the symbol is detected, the input is classified as an email address. Otherwise, it is treated as a phone number. This initial parsing step is straightforward and ensures the algorithm can apply the appropriate masking logic in subsequent steps. Once the input is identified as an email address, the algorithm proceeds to mask it. The first step is to split the email into two parts, the local name before the @ symbol and the domain name after it. For example, example@domain.com would be divided into example and domain.com. Next, the local name is converted to lowercase, and the masking begins. The first and last characters of the local name are retained, while all intermediate characters are replaced with 5 asterisks. For instance, example becomes E***********. Finally, the masked local name is concatenated with the domain, which is also converted to lowercase. The result is a masked email like *******@domain.com. This approach ensures that the email remains identifiable while protecting sensitive information. It's worth noting that this logic assumes the local name has at least 2 characters, as masking would not be feasible otherwise. For inputs identified as phone numbers, the goal is to mask all digits except the last 4. The first step is to remove any non-numeric characters, such as spaces, dashes, or parentheses, to extract the raw digits. For example, 123456789 becomes 123456789. The total number of digits is then counted to determine the format of the masked output. If the number contains 10 digits, it is formatted as ****************-1234, where the last 4 digits are preserved, and the preceding digits are replaced with asterisks and dashes. For numbers with a country code, which have more than 10 digits, the output begins with a plus followed by an asterisk for each extra digit. For example, +1 123456789 becomes plus **************7890. This step ensures consistent masking across varying phone number formats, with the input normalized to handle diverse cases. A closer look at the algorithm reveals several key insights. First, string parsing is central to the process. Email masking relies on splitting the input into parts, while phone number masking involves extracting digits. Normalization is another crucial aspect, particularly for phone numbers, as removing non-numeric characters ensures the algorithm can handle inputs in various formats. In terms of efficiency, the algorithm operates in O(n) time, where n is the length of the input string. This is because the operations, such as parsing, masking, and concatenating, require only a single pass through the input. The algorithm also leverages simple yet effective data structures like strings for input manipulation and lists for tasks like splitting and normalization. These choices ensure the algorithm is both fast and resource efficient, making it well suited for practical applications. The algorithm's implementation is optimized through careful use of string manipulation and normalization techniques. String slicing and concatenation allow masking operations to be performed efficiently, while removing non-numeric characters from phone numbers simplifies the overall logic. Robust handling of edge cases further enhances the algorithm's reliability, ensuring it can accommodate inputs with varying formats, such as different phone number lengths or uppercase email domains. For example, consider the email input example@domain.com. The local name is masked as E***********, and the domain is converted to lowercase, resulting in E********@domain.com. For a phone number like +1 123456789, the raw digits are extracted as 11234567890. The last 4 digits, 7890, are retained, and the preceding digits are masked, producing plus asterisk 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 dash 7890. These examples illustrate how the algorithm combines simplicity and efficiency to achieve accurate and consistent masking across different types of personal information. The solution begins by checking the type of the input string. If the input contains the @ symbol, it is treated as an email address. The email address is converted to lowercase to ensure uniformity, and then it is split into the name and domain parts. The name is masked by revealing only the first and last characters, with 5 asterisks in between. The masked name is then concatenated with the domain to form the masked email address. If the input is not an email, it is treated as a phone number. The solution extracts only the numeric digits from the input string, ignoring special characters like plus or dash. The last 4 digits of the phone number are preserved, while the rest are masked with a standard format of asterisk 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 dash. For phone numbers longer than 10 digits, which include a country code, the country code is masked with plus followed by the appropriate number of asterisks and a hyphen. The complete masked phone number is then returned. This approach handles edge cases such as varying input formats for phone numbers and ensures that the masking adheres to the problem's requirements. Here, we are implementing the solution to mask personal information in Java. First, we import the necessary utilities and declare our solution class with the maskPII method. The method accepts a string s as input, which could either be an email address or a phone number. We start by checking if the input contains the @ symbol, which indicates that it is an email address. If it is an email, we convert the entire string to lowercase to ensure case insensitivity. Then, we split the email into 2 parts, the name and the domain, using the @ character as the delimiter. The name is masked by keeping the first and last characters visible, with 5 asterisks in between. Finally, we concatenate the masked name with the domain and return the resulting string. If the input is not an email, we assume it is a phone number and proceed to extract only the digits. This is done by iterating through each character, appending only the numeric values to a string builder. The last 4 digits of the phone number are preserved, while the local part of the number is masked with a standard format of 3 asterisks, followed by a dash, then 3 more asterisks, another dash, and the last 4 digits. If the total number of digits is exactly 10, indicating there's no country code, we return the masked local part directly. Now, if the phone number contains more than 10 digits, we need to include a country code mask. To achieve this, we create a string builder for the country mask and start it with a plus sign. We calculate the number of asterisks required for the country code by subtracting 10 from the total length of the digits, and then append that many asterisks to the string builder. Afterward, we add a dash to separate the country code mask from the local part. Finally, we combine the country mask with the previously prepared local mask and return the fully masked phone number. This approach ensures that both email addresses and phone numbers are appropriately masked, while maintaining their distinguishing characteristics, such as the visible parts of the name or the last 4 digits of the phone number. To begin, we have an email address as the input, LeetCode@LeetCode.com. The first step is to check if the string contains the @ symbol, which confirms that it's an email. Once confirmed, we convert the entire email to lowercase to ensure consistency. This gives us LeetCode@LeetCode.com. Next, we split the email into 2 parts, the name and the domain. Here, LeetCode is the name, and LeetCode.com is the domain. Now, we need to mask the name by keeping only the first and last characters visible while replacing the middle characters with asterisks. Following this rule, the masked name becomes L*********E. Finally, we combine the masked name with the domain to produce the fully masked email address, L********E@LeetCode.com. This is the output for masking an email address. Here, we are working with a phone number input 12345678890. The first step is to check for the presence of the @ symbol. Since it's absent, we identify the input as a phone number. Next, we extract only the digits from the input, ignoring any special characters or spaces. This gives us the sequence of digits 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. We then check the length of the digits, which is 10, indicating that the phone number does not include a country code. Now, we mask the local part of the phone number by replacing the first 6 digits with asterisk 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 and keeping the last 4 visible. This results in the masked phone number, asterisk 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 dash 7890. This is the output when the phone number doesn't include a country code. Now we have a phone number input that includes a country code, +86 10 1234 5678. As always, the first step is to check for the @ symbol. Since it's not present, we identify the input as a phone number. We then extract only the digits from the string. In this case, the extracted digits are 8, 6, 1, 0, 1, 2, 3, 4, 5, 6, 7, 8. By checking the length of the digits, which is 12, we can see that the number has a country code, as it includes 2 extra digits. Following the masking rule for the local part, we replace the first 6 digits with asterisk 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 and keep the last 4 digits visible. This gives us the masked local part, asterisk 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 dash 5678. So far, we've masked the local portion of the phone number. Finally, we mask the country code portion of the phone number. The rule is to replace the country code digits with plus asterisk asterisk and then append a hyphen before the masked local part. For our input, the country code +86 is masked as plus asterisk asterisk, and when combined with the local part, the fully masked phone number becomes plus asterisk 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 dash 5678. This is the final output for masking a phone number that includes a country code. The time complexity of this solution varies depending on whether the input is an email address or a phone number. Let's start with email addresses. First, converting the string to lowercase has a time complexity of O, n, where n is the length of the input string, as every character is processed. Next, splitting the string at the @ symbol also takes O, n, since each character must be scanned to find the delimiter. Masking the name involves accessing specific characters and concatenating strings, which is efficient and takes O, 1, for character access and O, n, for concatenation. When we combine these steps, the total time complexity for processing an email address is O, n. This is because the dominant operations involve traversing the string, making the processing linear in time with respect to the input size. For phone numbers, the process begins by extracting digits from the input string. This involves iterating through every character to check if it's a digit, resulting in a time complexity of O, n, where n is the string length. Masking the local part, which consists of extracting the last 4 digits and concatenating the masked portion, is a constant time operation, O, 1, since the number of characters involved is fixed. If the phone number has a country code, constructing the masked country code involves generating a string of asterisks, which depends on the number of extra digits. This operation takes O, m, where m is the length of the country code, but since m is always less than or equal to n, this is effectively O, n. Therefore, the overall time complexity for processing phone numbers is also O, n. In both cases, whether the input is an email or a phone number, the dominant factor is processing the string character by character, leading to an overall time complexity of O, n. Now, let's analyze the space complexity of the solution. For email addresses, converting the input to lowercase technically creates a new string since Python strings are immutable, requiring O, n, space. Splitting the email at the @ symbol results in 2 substrings, each of which can take up to O, n, space in the worst case. Additionally, the masked name and final email string are also new strings, which contribute another O, n, space. Overall, the space complexity for email addresses is O, n, dominated by the intermediate and final string storage. For phone numbers, extracting digits results in a list of digits, requiring O, d, space, where d is the number of digits in the phone number. Since d is always less than or equal to n, this is effectively O, n. Constructing the masked local part in the country code also involves creating new strings, which require O, n, space. Therefore, the solution has an overall space complexity of O, n in both cases, as the additional space used is proportional to the size of the input string. Comparing this optimized solution to a naive approach highlights its efficiency. A brute force method might involve multiple iterations over the input string for masking, splitting, and concatenation, potentially leading to a quadratic time complexity of O, n squared, due to repeated operations. In contrast, the optimized approach minimizes the number of passes over the string, performing most operations in a single traversal, which ensures O(n) time complexity. Additionally, it avoids excessive intermediate data structures, maintaining an O(n) space complexity. When analyzing the algorithm's performance across different scenarios, the best, average, and worst-case time complexities all remain O(n), as the algorithm must process every character of the input string regardless of whether it's an email or a phone number. Similarly, the space complexity stays at O(n) in all cases, reflecting the memory required for intermediate and output strings. This balanced combination of linear time and space complexity makes the solution both simple and efficient, meeting the problem's requirements effectively. One common mistake when solving this problem is failing to identify the input format correctly. For instance, assuming that the input is always a phone number or an email without actually verifying the format can lead to incorrect masking. This is especially problematic when dealing with mixed inputs, where both emails and phone numbers are present. The fix here is straightforward: implement robust validation to distinguish between the two formats. For example, look for the presence of the @ symbol to identify emails, while phone numbers can be recognized by their digit patterns. Another frequent issue is not handling edge cases for phone numbers. Non-standard formats, such as those with country codes like +1 or +44, or those that include spaces and dashes, can cause problems. If these are ignored, your solution might fail or produce incorrect outputs. To address this, you should normalize phone numbers by stripping non-numeric characters and ensure that country codes are handled appropriately. This will make your solution more reliable and versatile. Another mistake to watch out for is inconsistent casing when working with email addresses. Email addresses are case-insensitive, but if you fail to standardize the case by converting everything to lowercase, you might encounter mismatches or incorrect results. The fix is simple: always convert emails to lowercase before masking them. Additionally, overcomplicating the masking logic is another pitfall. Writing overly complex code not only makes your solution harder to debug but also increases the likelihood of introducing errors. Instead, break the problem into smaller, more manageable steps. Focus on clarity by separating the validation, normalization, and masking tasks. This approach will make your code cleaner and easier to work with. Finally, many developers overlook internationalization when handling phone numbers. Assuming all phone numbers follow the same format, such as 10 digits for US numbers, can lead to invalid outputs for numbers from other countries. To avoid this, consider using libraries or predefined rules that are designed to handle international phone number formats effectively. When preparing for interviews, it's essential to focus on key insights. First, pattern recognition is a critical skill. Many string manipulation problems, including this one, involve identifying patterns such as the @ symbol for emails or sequences of digits for phone numbers. Being able to quickly recognize these patterns can save you valuable time. Another important aspect is considering edge cases. Interviewers often test the robustness of your solution, so you should account for scenarios like empty strings, invalid inputs, or unconventional formats. Also, while efficiency is important, clarity and correctness usually take precedence in these types of problems. Avoid trying to optimize your code prematurely; instead, focus on writing clear and accurate solutions. Lastly, always test your code thoroughly. Use a variety of sample inputs, such as emails with uppercase letters, phone numbers with country codes, and inputs that include special characters, to ensure your solution handles all scenarios correctly. If you're aiming to deepen your understanding, related problems on LeetCode like group anagrams, string to integer, étoile, valid palindrome, and restore IP addresses can provide great practice, as they share similar concepts like pattern recognition, normalization, and string validation. When it comes to implementing solutions, there are a few key alternatives to consider. Regular expressions, for example, can simplify pattern matching and validation. They are a powerful tool for identifying specific formats, but they come with the trade-off of being harder to debug and less intuitive for beginners. Another option is library-based parsing. This approach is particularly effective for handling internationalization and edge cases, as libraries often come with predefined rules and robust functionality. However, relying on external libraries increases your dependency on them, and they may not always be allowed in interview settings. Finally, there's the manual parsing approach using string operations. This gives you a high degree of control over the solution and is often easier to debug. The downside, however, is that manual parsing can become verbose and error-prone if not implemented carefully. Each of these approaches has its strengths and weaknesses, so choose the one that best fits the specific requirements and constraints of the problem you're solving. Great job! In summary, we covered the key aspects of masking personal information and explored an efficient brute force approach. Remember, problems like these emphasize the importance of string manipulation and secure data handling. Keep practicing, and don't forget to subscribe for more problem-solving sessions. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!